Welcome to AI Frontiers, where we explore the cutting edge of artificial intelligence and robotics research. Today, we're examining 12 extraordinary breakthrough papers that were all published on November 4th, 2025, representing a remarkable snapshot of where robotics research stands today. This collection showcases innovations that could fundamentally reshape how robots interact with our world, from humanoid robots learning through virtual reality headsets to surgical robots with superhuman precision. Picture this. A robot sits at a grand piano, its metallic fingers dancing across 88 keys with the grace of a concert virtuoso. In just one session, it flawlessly performs nearly 1,000 different musical pieces, from delicate Chopin nocturnes to thunderous Rachmaninoff concertos. This isn't science fiction anymore. It's happening right now in robotics laboratories around the world, representing one of the most spectacular demonstrations of robotic dexterity ever achieved. The precision required to perform classical piano pieces rivals that of professional human musicians, showcasing motor skills that genuinely challenge our understanding of what machines can accomplish. What makes this collection of 12 papers particularly fascinating is how they collectively paint a picture of robotics research accelerating at an unprecedented pace. We're not just seeing incremental improvements anymore. We're witnessing fundamental leaps in how robots perceive, learn, and interact with the world around them. These breakthroughs span from VR-trained humanoid systems to surgical precision robots, from flying manipulators to collective robot swarms that think and act as unified entities. This single day of publications provides an extraordinary snapshot of the current state of robotics innovation, suggesting that the field is experiencing a transformative moment that could reshape our technological future. To understand the significance of what we're seeing today, let's explore the landscape of computer science robotics. Think of this field as the brain surgery of technology, where the most sophisticated algorithms meet the messiest realities of the physical world. Unlike mechanical engineers who focus on building better robot bodies, or electrical engineers who design better sensors, computer science robotics researchers are the ones trying to give robots true intelligence. Imagine robotics research as a vast ecosystem, like a rainforest of innovation. At the canopy level, we have the big visible achievements like robots that can walk, talk, and perform impressive demonstrations. But the real magic happens in the understory, where researchers develop computational frameworks for robot perception, learning systems, and control theories. What makes this field particularly exciting right now is its emphasis on generalization, creating robots that can adapt, learn, and transfer knowledge across different situations, rather than performing single specific tasks. The first dominant research theme emerging from these papers is humanoid robotics and whole-body control. Think of this as teaching robots to move like humans, not just walking on two legs, but coordinating every part of their body in complex fluid movements. The Twist-2 system exemplifies this perfectly, providing a way to capture human movements through virtual reality and teach robots to replicate them with extraordinary fidelity. It's like having a master dancer teach their art to a student, except the student happens to be made of metal and circuits. This approach moves beyond simple bipedal locomotion to achieve integrated, graceful movements that coordinate multiple body systems simultaneously. The breakthrough lies in translating the natural, intuitive movements that humans perform effortlessly into precise robotic control systems that can replicate this fluidity and coordination. The second theme involves vision-language-action models, which are essentially teaching robots to understand the world the way we do, through both sight and language. Imagine trying to explain to someone how to make a sandwich over the phone while they can only see through a small window. That's the challenge these systems solve, but in reverse. They help robots understand both what they're seeing and what we're asking them to do, then translate that understanding into precise physical actions. This represents a fundamental breakthrough in human-robot communication, bridging the gap between natural human communication patterns and the precise control systems that robots require. These models enable robots to process visual information while simultaneously understanding linguistic instructions, creating a unified comprehension system that can drive appropriate physical responses. Our third theme focuses on dexterous manipulation and fine motor control, perhaps the holy grail of robotics research. This involves giving machines the same delicate touch and precise control that human hands possess. The piano-playing robot mentioned earlier represents the pinnacle of this research, demonstrating finger movements so precise and coordinated that they rival professional musicians. It's like teaching a robot to perform brain surgery while simultaneously conducting an orchestra. The technical challenges here are immense, requiring not just precise motor control, but also the ability to coordinate multiple degrees of freedom simultaneously, while maintaining the delicate touch necessary for complex manipulation tasks. This research is closing the gap between human and robot dexterity at an unprecedented rate. Now, let's examine the groundbreaking discoveries that emerged from this research collection. The first major breakthrough involves data collection efficiency that seemed impossible just a few years ago. Researchers have achieved the collection of 100 high-quality robot demonstrations in just 15 minutes, with nearly perfect success rates. Traditional methods might take days or weeks to collect the same amount of high-quality training data. This breakthrough is significant because data is the lifeblood of modern AI systems. The more high-quality examples a robot can learn from, the better it becomes at performing complex tasks. The second breakthrough involves unified vision motion codes, representing a fundamental shift in how robots understand the relationship between what they see and what they should do. This has been validated through more than 14,000 real-world experiments across 6 different robot platforms, demonstrating unprecedented scale and robustness. The third breakthrough comes from complex motor skills, where robots have mastered nearly 1,000 different musical pieces through large-scale learning, involving over 2,000 specialized AI agents and more than 1 million movement trajectories. Among all these remarkable papers, one stands out as particularly transformative: the Twist-2 system for humanoid robotics data collection. This research, led by Yangji Zhe and colleagues, addresses one of the most fundamental bottlenecks in robotics research, with such elegance and effectiveness that it could reshape the entire field of humanoid robotics. The story begins with a frustrating reality that has plagued humanoid robotics researchers for decades. Creating robots that can move like humans requires enormous amounts of training data, but collecting this data has traditionally required expensive motion capture systems, costing hundreds of thousands of dollars, specialized facilities, and teams of technicians. This created a vicious cycle where progress was slow because data was expensive, and data remained expensive because there wasn't enough progress to drive down costs. Twist-2 shatters this paradigm with an elegant solution that leverages consumer virtual reality technology, using PICO4U virtual reality headsets that cost a few $100s rather than hundreds of thousands, combined with a custom-designed robot neck costing approximately $250. The technical innovation of Twist-2 goes far beyond simply replacing expensive equipment with cheaper alternatives. The researchers had to solve fundamental problems in how to infer full-body poses from limited tracking points, how to translate human movements into robot commands, and how to ensure that the resulting data was of sufficient quality to train effective robot behaviors. They developed sophisticated algorithms that can reconstruct complete human poses from just head and hand tracking, essentially filling in the gaps with intelligent inference about how human bodies move. The real magic lies in the results. The system can collect 100 high-quality demonstrations in just 15 minutes, with an almost perfect success rate. To put this achievement in perspective, traditional methods might take weeks to collect the same amount of data, and the quality would often be inconsistent due to setup complexity. The researchers also developed a hierarchical policy framework that can control entire humanoid robots based on the collected demonstrations, successfully performing whole-body dexterous manipulation and dynamic locomotion tasks, with remarkably human-like behaviors. The implications of Twist-2 extend far beyond its immediate technical achievements. By dramatically reducing the cost and complexity of collecting humanoid training data, the system could trigger an explosion of research in humanoid robotics. Previously, only a handful of well-funded laboratories could contribute to this field. Now, any researcher with access to basic VR equipment and a humanoid robot platform can collect world-class training data. This democratization effect could lead to rapid acceleration in humanoid robotics development, Similar to how the availability of large-scale image datasets revolutionized computer vision research. The system's portability is another crucial advantage, as traditional motion capture systems require dedicated facilities with carefully controlled environments. The PRIS-2 can be set up anywhere, in homes, offices, factories, or outdoor environments, meaning researchers can collect data in the actual environments where robots will eventually operate, potentially leading to more robust and generalizable behaviors. By open-sourcing both their system design and collected datasets, the researchers are making advanced humanoid robotics capabilities accessible to researchers worldwide. Looking toward the future, the research directions emerging from today's papers paint a picture of robotics that's both exciting and transformative. Think of the current state of robotics research as standing at the edge of a vast ocean of possibilities. We've built impressive boats and learned to navigate coastal waters with confidence, but the deep ocean of truly general-purpose robotics remains largely unexplored. The trajectory suggests that the next few years will be marked by several key developments. First, we're likely to see the emergence of foundation models for robotics, similar to how large language models revolutionized natural language processing. These will be general-purpose systems trained on massive datasets that can be fine-tuned for specific applications. Second, the integration of advanced sensing technologies will give robots increasingly sophisticated ways to perceive and interact with their environment, moving toward robots that don't just see the world, but truly understand it through multiple sensory modalities. Third, more sophisticated learning algorithms will enable robots to acquire new skills much more rapidly, and with far less human supervision, approaching a future where showing a robot how to perform a new task just once enables it to learn and improve upon the original demonstration. The convergence of these trends suggests we're on the cusp of a robotics revolution that could be as transformative as the personal computer revolution of the 1980s or the Internet revolution of the 1990s. Robots are poised to move from specialized industrial applications into our daily lives, becoming as common and useful as smartphones are today. Perhaps most exciting is the potential for robots to augment human capabilities, rather than simply replacing human workers. The research examined today suggests a future where robots serve as intelligent partners, amplifying our abilities, and enabling us to accomplish things that would be impossible alone. Imagine a surgeon working with a robotic assistant that has superhuman precision, or a musician collaborating with a robot that can play any instrument with perfect technique. This represents a fundamental shift from automation that replaces human workers to augmentation that enhances human capabilities, creating new possibilities for human-robot collaboration that could reshape entire industries and aspects of daily life. Today's exploration of 12 breakthrough robotics papers reveals fundamental leaps in robot intelligence and capability that mark a pivotal moment in the field. The TWIS-2 system democratizes humanoid robotics research globally by making advanced data collection accessible to researchers worldwide, while vision-language action models successfully bridge human-robot communication gaps. We've witnessed superhuman precision achieved in specialized domains, from surgical applications to musical performance, suggesting that robots are beginning to surpass human capabilities in specific areas, requiring extreme precision. The research methodologies revealed, including large-scale reinforcement learning, hierarchical control architectures, and sophisticated learning from demonstration approaches, represent the evolution of how robotics research is conducted. These advances collectively point toward a future where the boundary between human and robotic capabilities becomes increasingly blurred, not through replacement, but through intelligent collaboration and augmentation. This episode was synthesized using GPT, Anthropic, CLAUDE-SONNET-4-20250514 for content analysis and synthesis, with Deepgram TTS for audio generation, and OpenAI for image generation support. All synthesized content has undergone human expert review to ensure accuracy and comprehensiveness. While every effort has been made to accurately represent the research discussed, potential oversights may exist, and listeners are encouraged to consult the original papers through the archive preprint server for complete technical details. The research papers examined represent the current state of robotics research, as published on November 4, 2025, and reflect the rapid pace of innovation occurring in this field.